Okay, so I thought I'd do another little pencast to help people get started on a few of the homework problems that I know people have been struggling with. So the first one I want to talk about is this problem from part 3 of the homework about open and closed maps. So let me just read the problem. It says a map from x to y, so a map from x to y is said to be open if the image of some open set O is open in Y whenever O is open in X. In other words, this is a statement about this map, and it says if you apply this map to an open set in X, you get an open set in Y. Notice that's different from continuity. It's not the pre-image of an open set in Y is open. So it's sort of going forwards. And then there's a similar definition for a closed map. And notice this is closed on the map, not on a particular set. And a closed map is one that if you have a closed set in X, its image in Y will also be closed. So let me suggest a way to attack this. So let's just consider the interval, let's say 0, 1, as a subspace of the real numbers. Now we have a map which I called I in class, from 0, 1 into R. In fact, we automatically get an injection map from any subspace into the superspace, right? And it's just the identity map. So such that I of x is equal to x, right? It takes 0 to 0 and a half to a half and 1 to 1. Let's say, notice that the set zero a half is an open set in 0, 1 using the subspace topology. But I applied to, well, I of this set 0, 1 half is, well, it's still just 0, 1 half, but now it's as a subset of the superspace of R is not open in R. So at least for this particular subspace of R, the injection map is not an open map, because the image of this open set is not open in R. And now consider, let's say 0, 1, the open interval, as a subspace of R. We still have a map I that maps 0, 1 into R, and it's essentially the identity map on those elements. So it maps 0, well, 0 is not part of the set, but it maps 1 half to 1 half, and 3/4 to 3/4. Now, notice, well, for example, that's not an example. Notice that the open balls in R intersected with 0, 1 give give sets of the form, well, there's a few possibilities. You can have 0A, AB, or B1, and the image of all of these is open in R. So I, the injection map, is an open mapping in this case. A hint for a closed mapping is look at the injection map with 0, 1 as a subspace of R. And just even a further set is, what are the closed sets in 0, 1? So that's something to consider, or should help you get started. Now let's see. There's a couple of parts to this, so give an example of a map that is open but not closed. I kind of talked about that. Hopefully you can get to that one now. So determine whether the projection map from R2 onto R sending XY onto X is closed or open. And for part B, just let R squared have the product topology then the open sets in R squared have the form U cross V, where U and V are open in R. So the projection map applied to, well, the projection map on the first component applied to U cross V is just going to be U which is open. That more or less answers part B, really. And then let's see, part C, do the same for this one. Again, the open sets in R are going to be, well, the basis for the open sets in R are going to be open intervals or open balls, and the you can look at what the basis elements for the topology in S1 are going to be, and I'll just draw a picture. These are the basis elements in R are going to be open intervals of this form, A, B. The open sets in S1 are going to be well, essentially open pieces of the circle. You can think of them as being from well, theta 1 to theta 2. And the image of these open sets here, you want to say whether they end up being open sets. The image of these open sets here, you want to say whether or not they're going to be open sets over here. So that's basically what it's asking, and you can draw some pictures to answer that.